Hello, my name is Leisha Howell Munson. I'm a second year PhD student in the Bioinformatics and Computational Biology department. Today I'll be talking about moving towards adaptive learning environments through the use of non-invasive neuroimaging. Here's a brief outline of what this presentation is going to end up looking like. We're going to start with the introduction, move into experimental designs, and then some of the analytical methods and what we have left to do. So for the introduction, we're going to discuss what personal learning or adaptive learning environment is, what is FNIRS, which is our neuroimaging tool, and why is all of this really that important? So an adaptive or personal learning environment is pretty much just like a digital space that students can use outside of the classroom or as supplemental teaching inside of a classroom to kind of get some more tutoring experience or learning experiments on different subjects. This is usually great for, as I said before, supplementing a classroom environment or also for self-teaching. This is often used through apps like Duolingo or through Khan Academy. And this sometimes allows users to set unique goals and direct their own learning journey depending on how advanced the personal learning environment is. Some fallbacks, however, is that these environments don't really have that like human touch to them. They're very difficult in trying to identify why a student is responding the way they are. So in a traditional classroom environment with a teacher working with the students, that teacher can usually tell when students are off task instead of struggling. But a personal learning environment will generally identify those two things as the same because it's taking in long reaction times or incorrect responses being like, oh, the student doesn't really know what they're doing right now. They need some more help. They need some more exercises on this topic. However, a teacher may see that they're just not even paying attention. They don't really care about the subject and maybe find some different ways to counteract that. Another thing is that they cannot really answer beyond what they're programmed to say. So especially if you have like free response questions, they can't really tell the student why they got something wrong. Usually that will be augmented by a teacher reviewing the work and kind of giving feedback that way. So what I mean when I say that we aim to augment these personal learning environments is that we're not going to replace how they function at the core. We just want to add in more data metrics such as neural data that will supplement the traditional ones, such as the response time. So at this point, the computer would be able to take in, oh, they took a really long time to respond. They maybe responded incorrectly. Why is this? And then they can kind of look at the neural data and be like, oh, they weren't really paying attention or focused on what was going on. So then instead of being like, oh, you don't know this material, it could suggest, hey, how about you go take a short break, kind of reorient your thoughts, come back and try again. So what is functional near-infrared spectroscopy, which is our neuroimaging tool? It's non-invasive. It's a cap that just goes straight onto your head with the probes attached there. Just needs contact with the skin. The light penetrates about 3 to 5 centimeters, which is just into the cortical region of the brain, which is the surface part. It can't go super deep into the brain, kind of like an fMRI would be able to. The units are also small and portable, as you can see by a student walking around with one on their back in kind of like a harness situation. And then most importantly, I want to point out what a channel is because it will be mentioned throughout this presentation. A channel is just the connection between two of the probes shown in the bottom picture. The red probe is what emits the light into the brain, and the blue probe is what receives that light and kind of detects how much oxygen is in the brain or in the blood, technically, at that point. So after that introduction, we're going to move into the experimental designs. I want to introduce you to how we're kind of accomplishing this goal in STEM environments and also language acquisition environments. In general, we follow the same approach no matter what domain we're working in. So we first want to use some well-identified validation tasks that have been used in psychology many, many times before in a strictly controlled environment to detect what neural regions we're interested in. So what regions should we really be focusing in right now? Then we move this into more of a realistic environment. So instead of using these strictly controlled cognitive tasks, we'll use something that a student may actually use in the real world, maybe not, but at least is like mimicking kind of the free flowing environment more so. It's not just like strict, you respond at this rate, the stimuli show up at this rate type of situation. And then finally, we move into phase three, where we integrate all of this data that we've collected to make a system that adapts itself based upon the user, whether that is with the neural cap still on the FNIRS cap or trying to use that behavioral and biomarkers that we discovered before and augment that into a system to maybe make better predictions, but without the use of a neural cap anymore. So specifically in the STEM education domain, we're currently in phase 2 right now, kind of borderline between phase 1 and phase 2. But the phase 1 was that we just used typical psychological tasks to induce a couple of cognitive states that we are really interested in, such as being goal-oriented, like having a specific problem in mind when you're doing the work, and mind wandering. So are you really kind of like just thinking about something else, things like that. Right now, we're finishing up that collection of the psychological task data and transitioning that over into an intelligent tutoring system to detect the cognitive states. So we want to see if the states that we detected in phase 1 are still detectable in phase 2 with something that's a bit more of a looser environment. And then phase 3 would be creating an informed intelligent tutoring system. So using that same system that we're using in phase 2, but figuring out biomarkers that may supplement the log data that the computer already collects. So maybe figuring out, oh, if they're pausing for this long of a time, it doesn't actually mean that they don't know what's going on, they're just distracted. So something like that. So we want to try and remove the neural input entirely in that situation, just supplement the behavioral data with neurally informed data from previous experiments. Then for the language acquisition domain, we're still in phase 1. This is a relatively new project that we started working on. And right now we're just trying to use validated controlled language comprehension tasks to understand the regions of interest when exposed to a foreign language. So that's already been well studied. We know that's Broca and Wernicke's regions. We're pretty much just confirming, yes, we can detect this with FNIRS, and also kind of expanding out of like, is this detectable in reading comprehension and auditory comprehension? And where do these primarily activate when it's a foreign language? So Broca and Wernicke's regions are for languages that you already understand. So where does it activate for languages that you don't understand? Is that just like random stimuli? What's going on there? Eventually, we'll transition into phase 2, which is the integration of the neural data into a self-study task. Not quite an intelligent tutoring system because it's not really tutoring anything, but just like a task that a self-learner may use to progress their learning journey, such as like Duolingo, for example, or Memrise, or Rosetta Stone. And then make sure that we can see that same activation from the validation tasks in the self-study task, and then also see what happens when they're progressing through more complex topics. Theoretically, on easy ones, it could very well activate in Broca and Wernicke's region because a lot of languages are similar to each other. So you can make a lot of predictions of what you're seeing. But when you get into really complex sentences with lots of insane verbs that don't really make sense, that's when we're wanting to see like that transition out of Broca and Wernicke's region. And eventually, this will all move into phase 3, which is to create an actual teaching system that predicts the user's proficiency in the foreign language and what subjects they're struggling in, and kind of augments their journey and changes what content they're seeing to learn based off of where they're struggling on. And this will be with the FNIRS cap still part of the equation. So this is going to be them using the system while using the FNIRS cap as well. So what are some of the validation tasks we've used? One of them is AX continuous performance task, or AXCPT. Excuse me. Its purpose is to identify cognitive states such as proactive control, reactive control, goal orientation, mind wandering. 1 second. So how this works is that participants may make assumptions on what they should respond to the second stimuli based on the first stimuli that they see. So the stimuli all come in pairs, as shown in the diagram above. And if they see an A, they're expecting to see an X, so they're going to press 2, whether they see that X or not. That's usually considered like proactive control, for example. And then what this is similar to is if you see a triangle with a missing side when you're doing some problems, you start thinking, what equation should I be using here, as shown with the triangle below. Which then brings us into the rule learning task, which is where you kind of think of like, how do you know which equation to use in that instance? You may see, oh, there's a missing side here. I want to try and do this equation, but why do you know which equation to use? So the purpose of this is to identify learning phases such as rule search, rule discovery, and rule following. There's an example on the right of what the participants may see and try and figure out what rule that is following right now. But pretty much the numbers will show 4 to 10 in sequences, and that will follow a rule at a time, and then it'll switch to a non-rule phase that's just random numbers showing up. And how this is kind of like in the realistic setting is that you go through a couple of problems where you see a triangle with a missing side, and you eventually learn, hey, I have two sides, it's a right triangle. This is Pythagorean theorem. So if anyone wants to say what that number is, feel free. And then finally moving into, for STEM education, the real world task that we're going to be using, it's a intelligent tutoring system called Assessments, which was actually made at WPI. Intelligent tutoring systems specifically are systems that provide immediate and customized feedback to the user. It's not just kind of automated with like, oh, this is this, this is this, this is this. So it has a little bit more of that human element to it of why someone got a problem wrong. And it also offers hints. So a lot of the time when you're using a personal learning environment, it may not give you any hints to what you could be doing in the problem. So on assessments, you can click, I need help, and it'll start giving you not the answer, but like the direction to start going in to get the answer. One of the ways that we are kind of mapping the physical responses of what we see students going through while working on these problems to their cognitive state, since we don't have any like identifiers that are easy to see, is that we'll use think alouds where the students explain what they're doing and why they're taking these steps to a cognitive action. So if they're going like, oh, I see this triangle, I have two of the sides and it's missing a side. I remember that a squared plus b squared equals c squared. So they may not technically be saying Pythagorean theorem, but they're saying the context around this rule that they've learned. So we kind of consider that like rule discovery. They've discovered what they're supposed to be doing, and then they're going to start following that. And then going into our language acquisition tasks, we have a reading comprehension task set up, which is to detect how the brain is activated when reading and writing a known language and a foreign language, both with familiar writing systems and unfamiliar writing systems. So participants will see words in English, French, and Japanese, which are the same words that you're seeing over on the side right now. And then they'll attempt to rewrite the word that they saw, rate the familiarity of the word, like if they understand it or not. And then it allows for differentiation between languages and writing systems, which is crucial because sometimes you can kind of tease out what a word means because you can read it. So maybe that will still process just because you can read what that says as language, whereas something that's completely unfamiliar like Japanese won't even register as anything. It'll just be like visual stimuli. This is kind of similar to the repetition of learning vocabulary in a classroom setting. So I at least remember back in school when I was learning Latin, we would have a list of vocabulary words and we just needed to look at the word, write it down, look at the word, write it down, rinse and repeat. This is kind of mimicking that a bit. And then just to sum up what we've gone through in these validation tasks, because it has been a lot, AXCPT is a task that allows participants to see stimuli in pairs. Each pair can correlate to a different cognitive state. So we have confirmed reasoning behind what the participant's brain is doing based on how they respond to these states. And there are 4 different cognitive states that we can detect primarily. Rural learning it shows participants sequences of numbers that may or may not follow a specific pattern. It's kind of mimicking how people learn new methods and how to apply new methods or equations that they've seen. Approximately 3 different learning phases that we're searching for in this. And Assessments is a WPI developed personal learning environment, specifically intelligent tutoring system that we're using to detect the previous cognitive states in a more realistic setting. And that we use the think alouds to map what the brain is doing to the physical responses that we can see. And then finally, our reading comprehension tasks is a task where participants will see words in 3 different languages, 2 of which will be completely foreign, 1 of which they should already know. We have 4 different categorizations that we're looking to obtain, and we can compare the participants' perceived familiarity with their expected familiarity, since we do take a response from them of if the word looks familiar or not. Next, we're going to start moving into our analyses, first with SPM-8. So I want to give an overview of what SPM-8 is, the results that we have received in language acquisition. So just big picture right here, without going too in depth into what SPM-8 even does, is that we wanted to look and see if a known language activates in the same area as words that are ranked as familiar, regardless of what language they came in. And then do foreign languages activate in the same area as words ranked as unfamiliar? So the 2 diagrams, pretty much so, yes, that is true. If we have a known language and familiar words, they both primarily activate in Wernicke's region, though they do go slightly in different directions on how much they activate there. And then B, we do have the same pattern for unknown languages and unfamiliar words, mostly in prefrontal cortex, which is the region in the top left portion, and then the visual cortex, which is the region in the back of the brain. So now that we can prove SPM8 works, what really is SPM8? It uses general linear modeling to fit the canonical hemodynamic response function. That's a lot of words. So the canonical hemodynamic response function, or HRF function, is shown on the right. It is pretty much kind of measuring the change in blood oxygenation based upon seeing a stimulus. So if you see something and your brain becomes more active because it needs to work through it, we'll technically see a decrease in oxygenated hemoglobin and an increase in deoxygenated because you're using up what your brain already has, and then a sharp increase of oxygenated hemoglobin because your brain's like, oh, I need to do this thing. Give me more oxygen to keep doing this thing. And then you'll see the decrease in deoxygenated because the concentration of the two has changed, the ratio of them has changed because of the increase of oxygenated. So how this works is that you compare two cognitive events and determine which one fits the HRF function better. And why we really want to know between two which fits it better is because if one fits it better, it correlates with more stimulation in that region, irregardless to how much actual oxygen concentration there is there. So it's not really dependent on, oh, we have a molar hemoglobin ratio of 4:1. It's more so looking at, did we see an increase at all? Like, does it follow the expected pattern that we're seeing versus how much is actually there? So in the reading comprehension task, how we set this up is that we used one participant with 19 unique channels. So remember, that's just the connection between the light emitting and the light detecting probes. And we had the two comparisons made that I've already talked about a bit. Going more in depth into that, we really just wanted to see if known languages truly did have a higher activation in Broca and Wernicke's regions. And also, do foreign languages have activation really anywhere? Are we expecting to see significance anywhere there? Which we did end up seeing. And then in addition, with familiar words, kind of the same question, that without respect to language origin, do they have the same activation patterns as the known languages? So an example, if you have a native English speaker who will they recognize the German word Musik, which just means music. It's the same word, one letter off, pronounced a little different. So going more in depth into the figures that I'd shown before, do foreign and known languages show unique regions of activation? Yes, they do. Figure A shows the region where known language was significantly active compared to unknown languages. So this is primarily in Wernicke's region, extending a little bit back into the visual cortex, whereas known languages did actually show some significance, as we saw before, in the prefrontal cortex and the visual cortex. So this is kind of maybe leaning towards, because we had Japanese in there, the participants saw the Japanese and their brain was like, yes, this is random visual stuff. So it activated a lot in the visual cortex, and then also in prefrontal cortex, that's an area that is often associated with learning. So it makes sense that there was activation there, that the brain was just trying to figure out what was going on. And then diving a bit more into familiar and unfamiliar words, they do follow the same pattern as foreign and known languages. When you map familiar words to a known language and unfamiliar words to an unknown language, as shown in the figures to the right. And then I also just wanted to point out that this is really small data set and really small instances of familiar words that were in a foreign language versus unfamiliar words in a known language. So there could have been not much impact shown there. It could have just been a bit more just overwhelmed by the familiar words in a familiar language and the unfamiliar words in an unfamiliar language. Next, into machine learning analysis, kind of an overview of machine learning and some of the results that we got during AXPT. This is more just to show that machine learning is a valid analytical tool for understanding neural data, especially in learning environments. So we wanted to validate its ability to classify different cognitive states, especially in time series, because time series can be a bit difficult to do with machine learning. So what algorithm is most suited for multivariate time series analysis from an skTime library, which is a Python library for machine learning? And does a certain train test split work best? So a train test split is how much of the data is used to train the model and how much of it is used to test the accuracy of the model. So we compared 4 algorithms to classify a goal following state and a loss of goal state in AXPT. Boss Ensemble had the best accuracy by 12%. It was in the 70s, I believe. We go into that more in depthly later. And Boss Ensemble's best iteration was with 70% of the data used to train the model. That was not the most amount of data that could have been used to train the model. So that was actually a little surprising to find, but really interesting. So machine learning and SK time in general, what are these things? So time series data is dependent on the preceding data points, and this correlation is lost in a typical algorithm. So if you use k nearest neighbors, how it's just standard out of the box designed, it would lose the correlation between the time points, which means that you lose pretty much every aspect of the time series data. You're just looking at kind of random changes in oxygen, if you will. SK time algorithms, however, are designed specifically to be used with time series, so it keeps that correlation. However, they're primarily used for univariate data, and neural data is typically multivariate. It's multivariate because we have many, many channels, up to 21 so far is the largest that we've used in our experiments. However, with other systems like EEG, you can have, I believe 64 is what it goes up to. So it kind of has a bunch of these different channels that are correlated to each other, so they can't be completely unique and distinct. You have to have that correlation there, and that gets lost in univariate algorithms. So you kind of have to warp them a little or use them in different ways to make them fit with these algorithms. The 4 algorithms we used are time series forest classifier, MR sequel, Boss ensemble, and K nearest neighbors. We can go into those a bit more at the end if you'd like, but just some brief descriptions there. So what did the data set look like for AXPT? We again used 1 participant because we didn't want to kind of cloud the system with too many different neural sequences. It contained 20 unique channels, and we have the 2 classes of goal following and loss of goal states from AXPT. So that's when they see an A and then they see an X and they press the second button for the X, that's goal following. If they see an A and then they see an X and they don't press the second button, they just press the first button, then they have lost the goal. They haven't really recognized that they were supposed to do anything different there. And then we randomized what data was used in the training tests and splits with 4 different iterations or 4 different split ratios. And then we repeated these ratios 3 times per split. So this included using 50% of the data in the training set, 60%, 70%, and 80% in the training set. Our results was that Boss Ensemble did the best, with K nearest neighbors and time series forest being kind of ranked similarly to each other. And MR sequel had barely better than chance accuracy, so that could have been negligible if it was actually better than chance or not. Our data, our classes were naturally balanced. We didn't have to oversample or undersample them to make them equal to each other, so chance accuracy here would be a 50-50. And then Boss Ensemble worked best, as I said before, with 70% of the data used as the testing set, not 80%. We usually would expect that with more training data being utilized, the algorithm would fit better. However, there are cases of overfitting an algorithm or a model, and that might have been what the case was when using 80%, as I overfitted to that specific data and couldn't really integrate new data in to predict better. Next, we're going to similarity search explanation. So we have a tool called BrainX. What really is it? Because it's not out in the world quite yet. How does it work? And what were these results for AXPT using, again, loss of goal and goal following, along with mind wandering in this state? So BrainX is a similarity search tool that is used for exploring specifically time series data, which is what makes it a little unique because it is designed specifically for time series, which is great for me. It clusters similar sequences together and pulls the best match out of the same cluster. What this means is that if you have a bunch of sequences, like let's say you throw 1,000 at the system, it'll pull them apart to figure out which ones match each other and group them together. And this makes it really, really fast when you're trying to query with a new sequence and figure out where it belongs or what it matches to, is that it only has to compare against, let's say that each cluster had 100 sequences in that original 1,000. It only has to look at 10 different sequences to figure out what it matches the best versus having to look at all 1,000. And then you can have a lot of customizability to it. So there's a bunch of parameters you can change, such as how similar the sequences need to be. What is your threshold cutoff there? for the clusters, what the length of similarity needs to be. So how much of the sequence needs to be similar? Can it just be like 10% of it can be similar, or does the entire sequence need to be similar? And then how many matches are displayed in your results when you send it a query and I'm like, hey, I want to see what's similar to this. I want to see 10 different sequences that look similar to this one. There's a couple of different ways that you can use it, such as interactive exploration, real-time querying, and using machine learning algorithms to search in a subroutine. We're currently only at the interactive exploration stage in this, and that's how this experiment's going to be going through. So in short, the results that we got for exploring the similarity of neural responses between self-report and mind wandering, so the participant going, yes, I am not on task, let me press this button to tell them I'm not thinking about the task, versus goal-oriented states. So since loss of goal could indicate mind wandering, so if someone's just sitting there pressing button one over and over and over again because they don't really care what they're doing, that could be similar to mind wandering because they're not thinking about the task. Will that neural state of the loss of goal be more similar to the self-report and mind wandering sequences than goal following states? So when they see that X and they go, yes, this is an X, I will press 2. So what we used to determine significance here was an unpaired t-test, looking at how far away they were from the query sequence, so the sequence that we're using as our example, with regards to the average distance. And our threshold was p equals 0.05 or 5%. Not 5%, 0.5%. Yes. So the data set used to determine if self-reported mind wandering and the loss of goal state are similar in shape. So this is just kind of what did our data set look like that we fed into the system to figure out what was similar and what wasn't similar. We calculated the distance between the two sequences using Minkowski distance metric, which is a combination kind of Euclidean and Manhattan distances. We had self-reported mind wandering as our search query, and we wanted the 5 most similar results. So what this really means is that we took all the instances that the participant told us that they were mind wandering, and we compared those to the data set, which had self-reported mind wandering, loss of goal, and goal maintenance or goal following states. And we wanted to see which 5 look the most similar. So in total, we had approximately like 300 sequences in there, and I wanted only 5 that were the most similar to my query. And we had hypothesized that the loss of goal state will be more similar to self-reported mind wandering than the goal following state. But what does it really mean when I'm saying similar? So below we have 2 figures. The one on the left is what similar sequences would look like. So they both have 2 peaks towards the later half. The 2 peaks may not be in the same part because that's one of the things that BrainX does, is that it uses dynamic time warping to allow the similarity to change where it is in placement in relation to time. But still seeing those 2 peaks is what's important here in this instance. Versus sequences that aren't similar are just one that's kind of like a straight upwards incline versus one that starts out pretty similar and then just completely changes how it looks. And then more in depthly into our results, we have 2 figures here. One is the loss of goal representation. So this is a query that had the most loss of goal results back. It had 3 out of the 5 being loss of goal. One was mind wandering and the other was goal following. And it had an average distance from its query of 0.9, which is quite low when using Minkowski. In blue is the query that we used. And in yellow is the only goal following result. And you can see that it starts extending itself out of the same range, whereas everything else is pretty clustered together. And then for a query that had only goal following representation, so all 5 of the results that came back were goal following, it had an average distance from the query of 2.84. So that's a difference of 1.9 in this distance metric between the loss of goal state and the goal following states. So that's kind of why we're able to see some instances of, that's why there was more significance for the loss of goal being similar to mind wandering than for goal following being similar to mind wandering. And you can see distinctly in this, that query in blue of kind of like oscillating a lot versus everything around it isn't really oscillating at all. It's just kind of in a downwards trend, which is why it was similar. And then finally, what are the next steps that we're taking and the main takeaways from this? So all of these analytical methods have their merits. However, they're not all a one size fit all. So SPM8 is great for a method that you want to compare against the HRF function when you're really specifically looking at when are we seeing this activation, the sharp peak in oxygenated hemoglobin. You can use SPM8 for that. It has successfully compared activation between known and foreign languages and between familiar and unfamiliar words. However, we haven't had as much success with the cognitive control states of like proactive control and reactive control, which I didn't really touch on in this presentation. For machine learning, we can successfully transform multivariate data into a univariate method. I didn't really mention how we did that too much, but essentially what we did is that we considered each channel a different data set and then had the algorithm vote across all of them. So each of them would be ran on the algorithm, say, I think it's this class or I think it's that class. And then whichever one had a majority vote would be what the algorithm classified it as. 3 of the 4 algorithms had better than chance accuracy, which is great. That is not always expected. And we were able to successfully classify loss of goal and goal following responses with the 77% accuracy, which isn't too bad of an accuracy for machine learning. There could be ways to get it up higher, but with Boss Ensemble, that had been done with tuning, which is kind of trying to finesse it into the best possible state. And then with BrainX, this method has the least restrictions on the data set. You can do pretty much anything with it as long as you have a data sheet to give it, which is good and bad. It's successful at identifying one channel where the loss of goal was significantly more similar to mind wandering, which is great. It means that our hypothesis could be true. We want to see this in more channels. We only used 4 in this instance. But yeah, so need to do a bit more exploration there. And it can be analyzed visually with plotting sequences or quantitative with reviewing distance metrics. Machine learning usually is just quantitative. You can visualize it, but it's not as intuitive. SPM8, you can have a quantitative representation of it, but again, it's not really that intuitive to do so. It's just a bunch of t-scores. So that's kind of where BrainX is better than both and being a combined system of the two. And then our next steps for the STEM education is to run rule learning this semester. So we only have that planned out. We haven't been able to run it quite recently yet. From this, we are hoping to identify those states and then move that over to mirror assessment spin clouds with our neurally collected data or neural data that is collected synchronously with it. So with that, we're mainly wanting to see if we see the same activation patterns for rule learning and for the cognitive control states. And then finally, we'd want to kind of tease out what biomarkers there are that relate to a behavioral state. And then see if that behavioral state can just be programmed into a personal learning environment. And then our next steps with language acquisition, kind of the same 3-step iteration, is that we want to run rule learning or run the reading comprehension task and then an audio comprehension task as well to see if there's differences there and a combined one. From that, we will create and run the self-study task in a digital environment to assure that we're seeing that same differentiation of signals. So seeing the more familiar parts of the language being in Broca and Wernicke's region and the more complex or unfamiliar regions of activation being in that visual cortex and prefrontal cortex. And then see if we can transfer this into a actual teaching environment that can look at the transfer from the visual cortex into Broca and Wernicke's region and be like, the participant is now learning this language adequately. They're familiar in this area, so they don't really have to be working on this. And that'll just kind of be a brain-computer interface that is whole to help teach languages. Thank you. And are there any questions?